Welcome. Thanks for coming. So I'm really happy to introduce Jacob Eisenstein, who's coming to us via bike from Pittsburgh. I kid you not. Although he didn't just get here like this afternoon by bike. He's been here resting for at least a day. So he's ready for the talk. So Jacob graduated a couple years ago from MIT. He was a Regina Barzilai student. He then went and spent a year with Dan Roth. And for the past couple of years, he's been a postdoc at CMU, working with Eric Zing and Noah Smith, and like a lot of students. I can't even name them. And he's starting in the fall, or not in the fall, in a couple weeks, a couple months at Georgia Tech as an assistant professor. So we wish him luck there. So Jacob's work started off by doing some cool Bayesian stuff with segmentation and gestures. And he's grown from there to do cool Bayesian stuff with a tremendous variety of different types of problems and different types of data. Recently, he's done some work with Twitter and sociolinguistics that's been really quite cool. He got a lot of attention for this. He got interviewed by Robert Siegel on All Things Considered, which is like living the dream as far as a lot of us are concerned. Although some of us, it would be Melissa Block, but whatever, it's All Things Considered. What I really think is very cool about all this work is it's really doing some really interesting stuff with linguistics, with very, very serious and very cool new machine learning stuff. And so I think that's what Jacob's going to talk to us about today.
All right, thanks a lot, Mark. Yeah, it's been just a blast to spend the day with you guys. So I want to tell you about some work that I've been doing. Since I've been at CMU, I've gotten very interested in social media. And alongside that, I've gotten very interested in sociolinguistics, which is trying to understand how language interacts with different kinds of social contexts. And I've found that a technique for machine learning, for learning sparse models, has been particularly relevant for this kind of work. And so that's what I want to talk to you about today. The title of the talk involves lexical variation, and this is a particular tradition within sociolinguistics to try to understand and quantify. It's one of the more quantitative traditions within linguistics, period. How language varies in different social settings and according to properties of the speaker. And so I think one of the sort of just really canonical, one of my favorite studies in variationist sociolinguistics is the study by William Labov in 1966. The social stratification of R in New York City. And what he found was this. He went to these department stores in New York. And he found that both between department stores, depending on how expensive the department store was, and even within department stores, depending on how expensive the items on the floor were, people would be more and more likely to use a rhotic R if things were more expensive. And not only that, people were more likely to use a rhotic R if their attention to speech was increased. So he would ask them where something was, knowing that it was on the fourth floor. And the first time they would say fourth floor, and they might not use a lot of they might not use a rhotic R, and then he'll ask them again, and it'll increase. So one of the things that this study shows that I think is really neat is that dialect. This is something that we think of as part of the New York dialect, but it's not purely geographical. It interacts with social factors such as income as well as the context of the situation. But what you might ask about this study is, how did he know? Oh, there's the picture. How did he know to study R in the first place? And so this just really relied on him having a lot of intuition about what aspects of the New York dialect were going to respond perhaps to these social situations. So essentially what's happening with quantitative sociolinguistics is that you're trying to focus on these kinds of associations between what Labov and others now call sociolinguistic variables, like the rhoticity of R, and attributes of the speaker or attributes of the situation, and so on. And if you think about this as an association problem, really there are millions of possible associations. I mean, there are thousands or maybe millions of things I could say about speech or written language, and thousands or maybe millions of things I could say about the speaker. I got particularly interested in this with respect to social media, and certainly these things are true in social media just as they are in speech. The difference is that in social media we now have access to tons and tons and tons of data in a way that was really not possible with traditional sociolinguistic methods. But out of all of these potential associations, again, how can we find the right ones? Now, a totally different way to look at so the sort of questions in red here are sort of to give you some intuition of how I came around to the idea of sparsity as a relevant technique for the kind of problems I want to solve. And I want to now motivate it from a totally different perspective, which I think should be clear to anybody that works on language technology, which is that language processing problems are inherently high-dimensional. And the more data you have, kind of the longer tail that you have. So this is just like the classic kind of Zipf's law type token curve for Twitter and Wikipedia. So you always have to do some kind of truncation. And so the question is, how can we control the model complexity with respect to vocabulary size, with respect to this inherent high dimensionality of language in a principled way? And in fact, this question and the question before about discovering relevant associations are sort of tied together. The framework we're going to use to do that is this framework of sparsity, which has become a really hot topic in machine learning in the last few years. And the simplest way to think about sparsity is in the context of a linear model. So I have some linear model where I have some labels, y, that are a matrix, and I have some features, x, or independent variables, x, that are also a matrix. And I'm trying to learn a set of weights that map between x and y, a linear model. And what sparsity says is that a lot of these weights are going to be 0 for a lot of pairs. And so really this solves maybe my association problem because it says a lot of associations are irrelevant. Maybe it solves some prediction problem I have in NLP by saying a lot of features are relevant for my prediction task. And the advantages of doing this are if you care about interpretability, if you're interested in the linguistic phenomena, this will help sort of focus your search. If you care about robustness, it's often been the case that sparse solutions tend to be more robust because they control model complexity. In addition to that, they have practical advantages. So sparse solutions can be lower memory, and they can be faster at inference time. What's nice is that there's been a lot of prior and ongoing work on sparsity. And maybe previously you might have had to sort of think hard about things like subgradients to get to use sparsity. But now there's just a ton of really easy techniques to do estimation of sparse models. This is just a little sample of that literature, but there's just a ton of stuff. So that's just sort of by way of introduction. But the outline for the rest of the talk, I'm going to start with an application, actually, towards understanding demographic language variation in Twitter. And then I'm going to move to a more machine learning-oriented methodological section on how to bring sparsity to Bayesian generative models. OK, so the first section, this is based on an ACL paper that I presented this year. And the highlights of this section is that we'll show how language and social media displays marked demographic variation. And I'll show how to use structured sparsity, which is a particular type of sparsity, to identify a compact set of words which act as demographic markers. OK, so Mark mentioned our work at EMNLP 2010, which got some attention. What we did was we took Twitter users in the US. So each of these points is a different Twitter user. And we looked at their text, and essentially we built a complicated Bayesian generative model, but essentially it's doing bi-clustering on their locations and their words. So you take any individual, and you say, well, what types of words are they using, where do they live, and how can I partition the country into dialect regions based on language differences? And so we're finding here that here's like the Los Angeles region. These people all live near each other, and they all use words that are kind of similar to each other. And so what words are those? They're words like coup and AF, and this is on Twitter. WID is like, what are you doing? This is like, for sure. So that's like nice. You can see this is like, it's like really robust. There are hundreds of people that use these things in Los Angeles. They don't use these all that often in other cities, even cities that have. So you say, great. We've learned something about Los Angeles. Well, like my in-laws are from Los Angeles, and they don't use any of these words ever. So, like what's going on here? And this comes back to how I opened the talk, which is that dialect variation, geographical variation, it's often aligned demographically. It interacts with demographics in a nonlinear way. And this is what I think Labov showed so elegantly with respect to social class and attention to speech in New York. But it's been shown with respect to a whole bunch of other demographic factors as well. These interactions are, of course, complex and nonlinear. And so we argue that it's crucial to model different demographic attributes jointly. And that's something I'll show how to do. This fits into a larger research direction recently, where there's a lot of work on inferring author demographic properties from social media content. So things like geographical location. We did some work in this area. There's some other concurrent work that got published at around the same time. Author gender, I think there's been some work here from CSLP on that topic, author age, and so on. And the contribution that this particular paper made with respect to this line of research, I would argue, is that we're able to do joint prediction of multiple demographic attributes from text, joint learning and feature selection. So essentially what we're going to be able to do is restrict the vocabulary of relevant words jointly while learning that relationship to demographic attributes. And then an exploratory analysis, which I think reveals some previously unknown things about how language varies with respect to demographics in social media. So the key, I think the key thing to start with to understand this research is how we were able to build data that allowed us to answer these questions. And essentially what we did is mash up Twitter and the US Census. So we receive a garden hose fees from Twitter for the first week of March 2010. This gave us 380,000 Twitter messages across roughly 9,000 authors. And each of these, the screen here was that each one of these authors had to have revealed their GPS location with their messages. So this is an option that you have if you post to Twitter from your cell phone. You can reveal your GPS location. Once you've done that, we can take that GPS location and find out what zip code you're in. And once we know the zip code, we know all kinds of demographic things about zip codes. So this is a unit that the Census Bureau uses to tell us things about demographics. And in fact, if you look at public health research, zip codes are very often used to proxy for demographics in exactly this way. Now, you do need to be careful because Twitter users are, of course, they're not an unbiased sample from a zip code. So if I know a zip code is 30% white, it doesn't mean that people on Twitter in that zip code are 30% white. We do know from other research on Twitter that it's among social media, it's quite balanced across different ages and across different demographics. But whether that holds to be true in our data set where we've made this requirement of having a GPS location, it's not clear. So these are really facts about zip codes, not facts about the individual authors at this point. There's other work that looks at author names. So you could enter your name in Twitter, and then once you have the name, you can go to the census and figure out things like race and things like age. And that's something that maybe we can combine with this data to get an even clearer picture. Just to give sort of an overview of the kind of data that we have, the mean author was from a zip code that was 52% white, 32% African American, and 16% Hispanic. So very diverse, more so than the U.S. population as a whole. And so these are the sort of demographic attributes that we're going to be trying to correlate with language. Race and ethnicity of the zip code, the proportion of people who spoke various languages. Urban is a census category that quantifies, their measure of urbanity in a zip code. In our data skewed very urban, so 95% of the people were from a zip code that was marked urban. But their threshold for urban is actually fairly low, so it doesn't mean that you're like downtown Baltimore to be characterized as urban.
And how did these compare to the rest of the country's average?
I know for race it's like 70% white, I think. I don't have any idea what it is for urban. Yeah. Right. But so these are the demographic attributes that we're going to be trying to correlate with language. And the way that we're going to set this up, again, is through a linear model where essentially we're multiplying matrices. And so you have some big matrix that I'm calling X, where you have term frequencies. Each author is a row. I'm calling the terms predictors. Each term is a column. I have another matrix. Again, each author is a row. The demographic attributes are on the columns. I'm calling these tasks. That's just sort of a terminology that's used in this multi-output regression. And what I'm trying to learn is this matrix theta that just gives me a linear map from term frequencies. So this is like the simplest possible model I could learn for this. And the way I'm going to learn this is by minimizing this function that basically has two components: a loss that says how well am I predicting the demographic attributes from the term frequencies, and a regularizer, which says how simple is my model for some definition of simple. But I'm going to try to solve this problem to minimize with respect to theta. And so the action really is in the regularizer. We're going to set up the regularizer in a way to yield an interpretable model. So I want to show you three regularizers. The first one is one you may be familiar with, an L2 regularizer, which just says the squared values of the elements in theta ought to be small. And what this does is it encourages small regression coefficients. And it's equivalent to just running if you know what a ridge regression is, it's equivalent to running a ridge regression separately in each column. So this can work OK for prediction, but is it interpretable? I would say no, because you're learning a non-zero value for every word demographic association. OK. So another thing you could do is apply an L1 regularizer. So maybe you know what this is. This says I'm going to penalize the absolute value of the components in theta. So this thing, it turns out that this kind of penalty encourages a lot of the coefficients to go to 0. And we can talk about why that is if you're interested. But this, again, is equivalent to running separate, now it's called a lasso regression, on each column separately. So again, you can sort of decompose this multi-output problem into a bunch of separate problems along each column. The third regularizer, and so is this interpretable? Sort of, right? We've instead of modeling every single association between words and demographics, I've restricted it to just a few. But it forces us to think about each demographic attribute separately. The third regularizer, and the one that we're gonna go with, is one called an L1 L infinity regularizer. And what this does essentially is it penalizes the max value in each row. So essentially, once you've selected a row to have even one non-zero value, you don't really pay any penalty for additional non-zero values in that row. And so what that does is it encourages this kind of stripe structure, where some rows will just have all elements be 0, and other rows are allowed to have all elements be non-zero. But there's not a whole lot of benefit to forcing elements. Once you have an element that's non-zero, there's not a whole lot of benefit to forcing other elements in that row to be non-zero. And so this is actually not equivalent to any decomposition of the original problem. Yeah?
Did you also consider group lasso on the rows?
Like L1, L2 or something? Didn't do it in this case. I think, subsequently we've seen some results that says L1, L2 would do really nicely. I don't think there's any particular reason. We had a nice fast inference technique for L1, L infinity. That's all.
I mean, the usual reason you use something like L1, L2 is they're mostly differentiable.
Right. Yeah, we had a technique that was, that was plenty sort of fast for this. But with either L1, L2 or with L1, L infinity, you're going to get the same property of having having row sparsity. So rows go to 0, and that's really what we were looking for. That's the interpretability that we're trying to get, because what it does is it isolates a few words that predict demographics and allows you to kind of throw out the rest. And I'll show you just how many we're able to throw out. So yes, I'll show you here, I guess. By increasing the strength of the regularizer, so we say how much are we penalizing. We had this penalty over the max of the elements in each row. By increasing the extent to which we penalize that max, we're essentially throwing out more and more words. And so you can see like the number of words on a log scale here on the x-axis. And then you can look at a measure of how well you're actually predicting demographics. And I'll get into the specifics of that measure in just a second on the y-axis. But what you can see is that basically, over here you're including all of the words and just doing some kind of post-fit ridge regression. And you can basically throw out more than 90% of the words and not lose any predictive performance. So you have a much more interpretable model without losing any predictive ability with this multi-output lasso. We compare to some other techniques. I'll tell you about this comparison in just a moment. So overall, yeah. So what I'm showing here is like Pearson correlation between the predicted and the true values of the demographic attributes. And using a dev set, we find that the best regularization parameter is at a vocabulary of, on average, 395 words. And you get predictive performance that's equivalent to the full model. We compare against other ways of reducing this input data. So you can do something like, let me just take the 395 most frequent words. That does pretty poorly. You can take the 395 highest variance words across authors. That does pretty poorly. You can do like a sparse singular value decomposition of the author term matrix. That does better than these two, but still not all that well. So this multi-output lasso, in terms of dimensionality reduction techniques, was far superior to these others. Now, in terms of the specific demographic attributes, as you can see, we can do a pretty good. So here I'm showing the average across all 10 demographic attributes. We can do better than that average on all three of the racial ones. So those turn out to be relatively easy to predict. And I'll show you the specific words that come in just a moment. On the language ones, we're also able to do pretty well, especially on English language. So I think English language is the highest correlation that we see. And the more socioeconomic ones are more difficult. So urban, percentage of people living in a zip code marked urban by the census, percentage of people living with their family in a zip code, and median income. These are pretty difficult to predict. All these correlations are statistically significant using like a Fisher confidence, a Fisher transformation of the correlation coefficient. The percentage of renters is the one socioeconomic one that we're able to predict pretty well. But overall, I guess the take-home is that by using this multi-output lasso, we get a 93% reduction in the model size. Rather than looking at 5,400 words, we're looking at 395 without any loss in performance. So in terms of a qualitative analysis, we're going to crank up that regularization penalty to select even fewer words. So now rather than saying 395 gave us the best predictive performance, but we're going to crank it up even further to just get down to 69 terms. And so that puts us somewhere over here on the x-axis. So performance is still pretty good, but now we have a very compact model where I can literally show you all of the terms. So just to start, I sort of broke up the terms into different categories just to make it sort of easy to look at. I think sort of the easiest place to start is in terms of place names. So Atlanta is a city. FAMU is Florida Agricultural and Mechanical University. It's a historically black college. And so you sort of see what you would expect. Positive correlation with number of African Americans. English language, it turns out. And so on. Spanish words, you get what you would expect. Positive correlation with number of Hispanics. And number of Spanish speakers. So this is just sort of to show that it doesn't give you something crazy. So it'll get more interesting. Standard English terms, in general, tend to correlate with the proportion of English speakers in the zip code, with this exception of this word dead, which is being used as an intensifier more often, like very, like I'm dead tired. So Twitter has a lot of these abbreviations. I showed you some earlier on. BBM is just BlackBerry Messenger, actually. But LLS is like, it's actually centered either here or Washington, D.C. Geographically, it's laughing like shit. And so this has a positive correlation with the proportion of African American speakers in a zip code, as do a lot of these other. So there's a pretty uniform demographic profile for all of these abbreviations. And these are literally like, these are the only abbreviations that got non-zero values according to the structured regularizer. SMH is like shake my head and so on. So this is sort of a uniform, fairly uniform demographic profile that we see for these abbreviations. And you can think about the kind of role that these abbreviations are playing as performing sort of a paralinguistic commentary, perhaps, on the content of the message. Like, my teacher said blah, 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 like SMH, and it's just like a commentary on what you've just written. Well, another way to perform that kind of commentary is through emoticons, right? So this is something that people very typically associate with computer-mediated communication. And what's interesting is that with respect, particularly to the proportion of African Americans in the zip code, you have exactly the opposite. You have exactly the opposite profile, where these correlate negatively. Right. The last set is sort of non-standard words, and the profile here is a little bit more varied. Some of the non-standard words tend to correlate with proportion of whites. Some tend to correlate with proportion of African Americans. In general, the patterning of whites and African Americans is pretty much opposite, which sort of fits what we know about spoken English dialects. That the sort of divide between African American English and English used by white Americans is one of the principal dialectal divides in spoken American English.
So
yeah.
I'm looking at a lot of these, and I'm very curious in the sense that if I were to look at this, it looks like our African Americans, the column for renters and African Americans line up very closely,
Yeah.
not only on this but on some of the other charts
Yeah.
we showed, which I find, I don't know, but that's interesting.
Yeah, I mean, you could look directly at the demographic data to see what the correlation is between those, and maybe that's I think it's not unlikely that I think and renter is an interesting one because it's the only socioeconomic one that we're able to predict all that well. So it might sort of correlate with low income, high urban. Right. It may actually tell you more about income than it may actually tell you more about wealth than income does, right? Because this is sort of relative to the place that you live in a way that renter's not. Yeah, Mark.
So I was going to say, renter is, as you were saying, very location specific. So if you're looking at areas that have lots of apartment buildings versus homes, you're going to, so
Yeah.
it might be approximate location. But I was going to ask another question. So you said you're going to go down to 59 or 60 or whatever features. How different are these than if you had just taken the 500 features and looked at the highest valued features or something?
Or at the other extreme, if you'd boiled down to just one feature. So if you've done these correlations independently, what you're looking at, these plus and minus here,
Right.
positive and negative weights, right?
Right.
It's not quite the same as saying that this word is correlated.
So the plus and minus are actually from like a separate, like a post hoc test where we're comparing the means of the demographic attributes for people that use and don't use the word. So the words were selected by having non-zero values according to the regularizer. But then the plus and minus are this sort of post hoc comparison where we're doing this sort of multiple.
Plus and minus would be the same under mark similar.
Well, the difference is that you have to do this multiple comparisons correction too, right? So here we're only doing a couple hundred significance tests. There we'd be doing many thousands. And so you'd have to throw some out. Yeah, you'd have a higher threshold. Yeah. Okay. Okay, so yeah, I think I've sort of covered these points. But it's interesting that paralinguistic commentaries performed with emoticons more often by Latinos and less often by African Americans. Abbreviations tend to be correlated, tend to be performed more often by zip codes with African Americans, and again with Latinos. And then a lot of these sort of phonetizations seem to correlate with the proportion of African Americans, right? So a lot of these things this is like over, a lot of these sort of phonetizations correlate with the proportion of African Americans in the zip code. And it may be interesting to see if some of these phonetizations actually reflect phonological features of African American English. So that's something I plan to look at going forward. But that wraps up what I wanted to say in the first part of the talk. I think that the take-home is, first of all, by mashing up these geotagged social media messages with census data, we can study the demographics of lexical variation, at least, on a very large scale. And we're able to do that here just by doing a linear regression with the structure sparsity that reduces the size of the vocabulary. Any more questions about this before I move on to the next part? Yeah.
Could you try to version your model? Just a hierarchical model with your group means and their deviations from that, where you decide on a group based on a region.
A group of authors?
Yes. So the idea is that you'll capture deviations from local trends. So if most people in the city rent, it might not matter that the city.
But remember, I don't know anything about individual authors, right? I know what zip code you're from, and then I know the proportion of people that rent in your zip code. I could compare that zip code to the city as a whole if you're in a big enough city to have, to some other bigger group, I guess, like some bigger cluster of zip codes. Yeah, that's an interesting point. So then you would know, because I think we have this problem with income that like a high income, in one place is not necessarily a high income, in New York City or something, and that might get at that.
And it also gives you two effects to analyze: local effects,
Right.
as well as just this city has this amount.
Right. Yeah, and the intersection of this stuff with geography also is something for us to look at, going forward too. Yeah.
So two questions. So you said you used the GPS data. So does that mean that the same user could be bucketed into different zip codes if they're like tweeting from different locations?
We took the mean, and it was people moved shockingly little in this data. So.
Okay. Because like a common thing is everyone goes to work during the day.
Yeah.
And so you have lots of tweeting in the cities, and then
Yeah.
some move out at night and some don't.
Yeah. We had very few people that were in different zip codes across a number of the mess. And I think, honestly, like looking at this text, and I don't have any like evidence for this, but looking at the text, a lot of these people seem, just based on the content, they seem to be young, right? So people seem to be writing about stuff like school, stuff like their parents. No, in school and writing about their family and stuff like that. So, it may be that these are like, that these are, I mean, you could imagine sort of the profile of someone who would choose to reveal their GPS coordinate with every message. That might be more likely to be a high school student or something, or a college student. Yeah. Yeah.
Well, the other question I wanted to ask, you probably don't have an answer, but so you showed a bunch of these patterns and which tokens light up, which just different demographics. So why? Like, do you have any idea like why this is the case?
So I think, I mean, I don't have like a single answer for everything that we've seen. Obviously, I think that as I said, the sort of phenomenon of whites and blacks patterning almost opposite each other on almost every item, sort of really mirrors what we know about spoken English in America.
But why like emoticons?
Why emoticons versus that's I think that's impossible to. I mean, emoticons also pattern. I know this from other research that we're doing now. Also pattern female, and there's prior research on that too. And there's a lot of, if you go into the sort of stylistics research in sociolinguistics, there's a lot of research on sort of relationship between masculinity and different. So, there's a lot of room, I think, to do sort of theoretical work about these kinds of results. Yeah.
Okay.
Yeah.
So I do wonder whether you might be able to do a better job of eliminating compounds. Here's why I'm a little worried about compounds. Let's take an example. So I noticed that all these English acronyms are associated with Hispanics.
All the English acronyms are associated with Hispanics?
Yeah. And I wonder if that's because English acronyms are associated with African Americans, and African Americans are associated with Hispanics.
Oh, yeah. I mean, yeah. So do you have an idea about how to tease that out?
I think I could work it out. Yeah.
Okay.
We can talk that out.
Yeah.
I don't want to try it here.
Yeah. Okay. Yeah.
Do you actually have the breakdown by age group in the zip code of the demographic?
So zip codes can be really homogeneous with respect to demographics. They're less homogeneous with respect to age. So we didn't. I actually don't know if that information is available from the census, but that's not something we tried to look at. I think you can do a much better job making guesses about age based on the author name, and that's not a feature we've looked at yet, but it's certainly one that's available. Yeah.
So, can you track individuals at all? Can you see if they're consistent in their vocabulary depending on who they think they're broadcasting to?
That's the question that actually we're looking at now. So we have data, in fact, over 2 years. And we know things like you can make guesses. So we're looking at this with respect to gender, in fact. So we know you can make guesses about people's gender based on their name that are pretty accurate. And you can also say something like, who does this person usually write messages to on Twitter? And are those people usually women or men? And how does that, and if they are specifically writing someone that we think is a woman or a man, and they're a woman or a man, how does that sort of change? So that's sort of in progress, I guess, as we speak. Yeah. Okay, so I want to move on from the sort of application linguistics-y part to a much more machine learning-oriented part of the talk. And here, what we're interested in is bringing this idea of sparsity now to generative models. So I've shown you now before just really the simplest kind of model you could think of, a linear model where you're just learning a linear map from word frequencies to these demographic features. But in fact, we have this whole family of generative models over text. And these enable these sort of latent variable representations that have been a really powerful tool. They can help us do things like beyond sort of naive-Bayes clustering and classification, discovering latent themes in document collections, and even sort of combining things like manual labels with latent themes in things like topic aspect models. And so this research here is how to incorporate sparsity in arbitrary generative models like this. So the unifying idea of these sorts of generative models over text is that each class or latent theme is represented by some distribution over tokens. And your estimation problem, essentially, is to estimate this distribution. And that's, in fact, what I want to argue against in this work. And there's sort of three things that I can tell you that are wrong with this idea. The first is redundancy, and that's that. Imagine you have a naive Bayes classifier, and you're trying to classify 20 news. Well, you have to estimate the parameter. What's the probability of generating the word "the" for every single class Y? Do you really need to be estimating that parameter all those times? This is really a fact about English and not about any of the classes. People tend to deal with this problem through heuristic techniques like stop-word pruning, but these are hard to generalize when you want to move to, just already moving to Twitter data from Newswire data. Typical stop-word techniques often don't work all that well. So we argue it would be better to focus computation on the parameters that actually distinguish the classes. And this is really the advantage of discriminative versus generative models. A second argument against these sorts of generative models is related, but I would say slightly different, over-parameterization. So imagine you're training a topic model, a latent Dirichlet allocation model, with k topics and v words. So you're estimating k times v parameters. Well, then you write the paper. How many of those words do you actually show in the paper? You show about 10 words per topic. So essentially, you have all these other parameters, v minus 10 words per topic, that you don't even really maybe see. You may not see them, but they're doing something, right? They're affecting which documents get assigned to which topics. And there may not even be enough data to estimate them accurately. And in fact, I'll show you that there isn't. The final problem that we want to address with respect to typical generative models has to do with these more complex models where you combine latent things like topics with observed things like labels, like ideology, for example. So, and this is a point that's maybe a little more specific to this literature. But imagine that you're building a model that combines something like topics and sentiment. Typically, the way this is done is by adding a switching variable that just decides, is a word going to be drawn from the topic, or is it going to be drawn from sentiment? But what you've done now is you've added twice as many. You've doubled the number of latent variables that you have for each document. I'll explain this in more detail when I get to this section of the talk in just a minute. So the change. So essentially, again, what's happening in typical generative models is that you're estimating the probability of each word type with respect to each label or each topic. And we want to just make a small change to this idea. That rather than estimating the probability of a word given the topic, you estimate a difference in log probability from some background distribution over English. So I hand you some background log probabilities of every term in English. And then you say, OK, for this topic or for this class, how do the log probabilities differ? And that's something that I can just add in log space here. What's advantageous here is that this eta now can be sparse. So it can be mostly zeros. And if I have additional facets, if I want to do something like combine topic and sentiment, I can just add things up inside this exponent. I don't need that switching variable. So I'll show you how this works in detail now. Yeah, just to maybe hammer home that point about switching variables. Imagine that you were trying to build a model that combined topic and ideological perspective using a standard sort of Dirichlet multinomial technique. You might have essentially, you'd have to have some switching variable that shows these are the models and these are the distributions over words, and I choose which one is active to generate each token. And here what's happening is we're just adding them up in log space, and we exponentiate and normalize, and we get a word distribution that way. OK, so what we mean by sparsity in this case is that these differences from the background log probability are going to be 0 for most word types. It's important to keep in mind that because we're going to be normalizing, just because eta I might be 0 doesn't mean that the probabilities are the same. But what is the same is the log odds for words where the etas are 0. This is a very different notion of sparsity from the sparse topic model, which is something that we saw from Chong Wang and Dave Bly a few years ago, where you have this notion of sparsity where you're actually setting the probability of a word to 0 for many words. I would argue that sort of, you lose this advantage of robustness in this model because any word can basically veto a topic or can veto a class if its generative probability is 0. So here we're saying, rather than making the generative probability 0, we're making the difference 0. It's a little technical, so I think I'm going to, well, now I'll tell you how this works. So I mentioned this L1 regularizer earlier, where essentially what you're doing is you're penalizing the absolute value of the weight for a word. And that turns out to be something that induces a lot of zeros in the distributions that you have. The L1 regularizer, it turns out, probabilistically, it's equivalent to something called a Laplace distribution. And a Laplace distribution, it turns out, is equivalent to this integral where you have a normal distribution with some variance. The variance has a prior that's an exponential distribution, and you marginalize out the variance. And this is an equivalence that's been known for at least 20 years. So this gives you some sense of how you could have sparsity in a generative model. What's nice is that it turns out that other integrals also induce sparsity. So you don't, the prior on the variance doesn't need to be exponential. In fact, if it's gamma, that will induce sparsity. If it's a Jeffreys prior, which is a non-parametric prior, that will also induce sparsity. So what this says is just by solving this integral, and now it's parameter free, I can still get an eta in the end that's sparse. In fact, what we'll see is that you get adaptive sparsity, meaning that you get about the amount of sparsity that's justified by the amount of data that you have. So we're going to solve this integral through coordinate descent. We're going to update a variational distribution around tau. And then once we've done that, we're going to maximize a point estimate for eta.
So
Yeah.
I'm just wondering, so you're aiming to solve the L1 regularization around the point, around the pivot point, which is your background model?
Yeah. 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 So you can assume the sort of background log probabilities are just given to you. You could estimate. I mean, you could do sort of an iterative thing where you're estimating them jointly, but I don't think that would change. That would change much. Yeah. Is that helpful? Yeah.
I just want to make sure I understand what's going on. So the first of all, you're still doing math estimation, right?
Yeah. So this is an important point. We're not fitting some distribution around eta. This is more in the spirit of the original LDA, like empirical Bayes. We're just estimating eta.
And otherwise, you wouldn't get sparsity.
That's right. That's right.
And in order to get sparsity in math estimation, all you need is for the log power to have this sort of
Yeah.
error.
Yeah.
So that's why lots of integrals will get it to.
Yeah. Yeah.
And in this case, you don't happen to be able to do. You don't happen to be able to do math inference in closed form, but you can still do coordinate ascent.
That's right. Yeah. That's right. That's right. So you can just do like L1 estimation of eta, right, using some like soft thresholding trick or something. And that I've done this in this model, and that also works. But what's nice about this normal Jeffreys thing is that it's parameter free. You don't actually have to say how much sparsity you want. Yeah. Okay, so I applied this in 3 different types of models. I don't think I'm going to get through them all, so maybe I think it's easier to understand, though, in the context of just a naive Bayes classifier. So maybe I'll go through that one in detail and definitely ask questions if there's any confusion. And then I'll wave my hands a little about the other 2, if that's all right with you guys. So the graphical model here is that every document, this is a plate over documents indicating repetition. Every document has a label, YD, that says what class it's from. So in 20 news groups, maybe the class is, I don't know, rec, sports, baseball, or whatever. And then you have another inner plate over words. The words are, again, observed, so each word is a token. And we're building a generative model over those word tokens. I'm assuming that the background log probabilities for each word are just given. I just estimate them from my frequencies at the beginning. And so what I'm trying to do here is estimate these etas and jointly this tau, which controls their variance. I'm just sort of being completely explicit and writing it all out here. Right, so you can equivalently think about a multinomial distribution for each class that has this form, right? Just a normalized exponent of the sum of the eta and the m. And again, the prior on this tau variable is just this Jeffreys prior. So it says smaller variances are more likely. I think yeah, so you can basically, you're going to do this. There's a variational bound that we're going to be maximizing, if that's helpful to you. And the gradient with respect to that bound for eta has this really intuitive form. You have the observed counts for the class or for the topic. You have your expected counts. And then you have some penalty that's associated with the regularizer. Move ahead a little. So how does this work? We took the 20 news group beta. This is just a 20-way classification task. And we start out with the entire data set. And we were just comparing against naive Bayes with a Dirichlet prior, where the Dirichlet prior is just re-estimated. So you're doing sort of typical maximization with respect to that Dirichlet prior, and you just iterate. So you do a little bit better when you have the full data. But as you remove more and more data, the advantage of the SAGE approach really starts to show. So when you're down to 5% of the data set, SAGE is really far superior. You see multiple points here for multiple initializations, because this is a non-convex optimization now for both procedures. So again, we're sort of getting that robustness advantage that I talked about earlier with respect to sparsity. You have very little data. You have a high vocabulary. The Dirichlet prior does a poor job controlling the model complexity, and SAGE gives you much better performance down there. Now, I made this point earlier about the Jeffreys prior and what I call adaptive sparsity. And what's interesting is that if you look at training on the full training set, so I have 11,000 documents, about 10% of my parameters are non-zero. If I reduce the training set size down here, where I have only 550 documents, the number of non-zero parameters goes way down to 2% because it just has less data, so it's not able to estimate those things accurately. Yeah. We just use the same vocabulary. Yeah, it's a fixed vocabulary. You just may not have any counts in the training data for. Yeah. Yeah. Yeah, that's a good point. That's a good point. I should probably correct for that. Okay. I'll tell you a little bit about how this works in topic models, and then maybe I'll wrap up. So this is sort of, if you're familiar with like the LDA topic model, essentially, again, you have a plate over documents. Each document has a set of latent topic proportions. I've written theta d up there. Then you have an inner plate over words. Each word is drawn from some latent topic written ZD, or it should be ZDN for that particular word. And what we're saying is that rather than each word being drawn from just a multinomial, it's drawn from this stage distribution, this exponent, logistic multinomial is a way to think about it. And so if you're with me when I presented that gradient earlier with respect to naive Bayes, it's basically the same thing here. You have expected, but instead of having the observed counts, now I don't know the actual z for any particular word, so you have expected counts under my variational distribution, and expected counts under the sage model. And you want those things to balance out. So I really want to get to the next graph, but what we did is we ran this on the NIPS corpus, which is just like a typical benchmark people use for topic models. And what we found was that when you have only 10 topics, Sage and like a standard Dirichlet multinomial LDA do about the same. As the number of topics increases, you have less and less data to estimate your parameters accurately, and you get more and more of an advantage with Sage. This is my favorite graph, though. So, right, and this adaptive sparsity point again. When you have only 10 topics, about 5% of the parameters are non-zero. When you go up to 50 topics, 1% of the parameters are non-zero. So what that means is actually the number of non-zero parameters is exactly constant, close to exactly constant in these two settings. You have 5 times as many topics, but 5 times fewer non-zero parameters. And what we measured here was, so we broke all the words into quantiles by frequency. And we said so that the 10% of the words that are most frequent, the 10% next frequent, and so on. And then we said, what proportion of the total variation in each topic is accounted for by each quantile? So we thought that when you run standard LDA, it would be a pretty much flat curve. The standard LDA would sort of assign the same amount of variation for low-frequency words as for high-frequency words. So in fact, it's even worse than that. So standard LDA puts the most proportion of the topical variation on the 10% of the words that are the least frequent. So it's essentially saying, if you don't have a lot of data, this is like really the worst thing you can be doing because you don't have enough data to estimate these parameters accurately at all. Sage, on the other hand, basically says for the bottom 3 quantiles, I don't know enough about these words. I'm setting those parameters to 0 every time. And I'm going to reserve the variation that I have for words that I see often enough to make a good estimate. And I think that gives some intuition about what's happening here. So I'm going to skip this part and wrap up, since I think it's been about an hour, if that's cool. Essentially, we built more complicated models that combine both latent topics with observed labels. For example, the location of an author on Twitter or their political ideology of a blog. And we found that by combining latent topics and these kinds of labels, by just adding in log space, we're able to get good results. And this is a much simpler model than a model that has a switching variable that has to choose between these aspects. So just to summarize this part of the talk, when we build generative models, people really like this Dirichlet multinomial pair, and it's computationally convenient. It's really easy to do collapse sampling. It's really easy to do estimation. But I would argue this Dirichlet multinomial pair really doesn't control model complexity adequately. We've presented an alternative here called the Sparse additive generative model, and I would argue it sort of has these nice criteria. It gracefully handles extraneous parameters, It seems to control sparsity pretty well without even having to provide a regularization constant. And in these multifaceted models with like topics and aspects, it seems to facilitate inference. So overall, language is inherently high-dimensional. I think we all know this. And controlling model complexity is really important, both for robust performance on held-out data, as well as interpretable models that yield linguistic insights. So with respect to this analysis of demographic variation, we use this L1 L infinity norm that allowed us to reduce the vocabulary by over an order of magnitude while preserving accuracy and make some insights about what was going on. Then we showed how to do this in generative models. So that's it. I think I'll wrap up. Thanks.
So, only a little. But, so essentially what you're doing, though, is identifying words that have non-zero parameters. And that's a sparser set of words. So when you actually apply this to topic detection, you just look at those words then, or do you actually try to generate the words, all the words?
So you generate all the words. Yeah, you generate all the words. But most of the words are generated just from its background frequency in English. So you have some topic, and this is the topic associated with computational linguistics presentations. But a lot of the words that I use don't actually have much to do with computational linguistics, right? They just are just going to be generated according to their frequency in English. And it's only the ones that are really particularly distinctive for this topic that are going to come into play. Yeah.
But to do the detection, it says this was probably...
You use all, yeah. So the naive Bayes experiment was basically like a text classification experiment like that. So you have like 20 classes of things like sports, technology, and so on. And you use all the text. But you've learned that only a small subset of the words are actually relevant to this classification task. Yeah. So there's a lot of research on on sort of feature selection. And you can build these pipeline models where you do some kind of feature selection, and then you do training. All of this stuff, and maybe I should have put this in earlier, all this stuff is sort of under the rubric of doing feature selection and learning jointly. And the idea is that that's preferable. Yeah. Yeah.
So I apologize if I misunderstood like this, but you're putting these two topics together, if you think of things in this way. So you're in Sage, you're learning for each topic, you're learning its deviation from background.
Yeah.
So if you think of each one of those as a vector, and now you want to build a matrix out of it, and you've got a matrix like you had in the first part of your talk, now you want to learn sparsity across that matrix. So we want to motivate how we're choosing words for topics based on how we're choosing words for other topics.
That would be an extension for Sage, right? So you could say something like, rather than saying each topic should only be about a few words, you could say something like all topics should only be about a few words. And that would get you back to the kind of thing I was doing in the first section. The first section was a simpler model in the sense that it was just a linear model, whereas a topic model is a latent variable model. And it's more complicated for that reason, but you could absolutely take the same sort of multitask sparsity trick and apply it there. Yeah. Yeah.
Well, yeah. This is kind of related to Travis's comment earlier, but I guess there's a hierarchical thing you can do, right? Where this background, like you said, the probabilities for a computational linguistics talk is not the same as the background. That's just generic English, and that would be those would have some deviation from. So like the distribution for computational linguistics talk would be like some deviation from the generic English distribution.
Mm-hmm.
And you could, I don't know. Have you looked at any modeling that takes into account a deeper hierarchy?
Yeah. So 20 News is actually a good domain for this because there's like an inherent hierarchical structure. It's like based on these old school news groups. So it's like, you have rec.sports.hockey and rec.sports.baseball. And so they're, you would think that maybe those should be more similar to each other than, the topics about, the classes about like Linux and, or Unix, I guess, and Windows. And I actually did try this, and I don't remember if it helped or not for that case. But certainly Sage allows you to, because you're just adding stuff, it allows you to do that kind of thing. In fact, we did do this for geography. So we would say something like there's like a northeast region, and then within each region there are like specific models for specific cities. And you can do hierarchical models like that. I don't think I ever tried that as like a prediction task. So I don't have like numerical results for how it works. But the things that you see seem to make sense. So, yeah.
The words that come up, are they also the ones that have the highest variance in the whole data set?
I don't know. That's a good question. In the first part of the talk, we compared against a baseline of just selecting the highest variance words, and you do better than that baseline. In the second part of the talk, it seems like we're getting words that are more frequent in general, but I don't know, how it relates to variance. It's a good question. Yeah.
Yeah, I forgot. I'm curious about. So, in the original LDA paper, they listed those top K words for their topics, to show the topics, and Jordan was here a few weeks ago talking about presenting topics and making them easier to digest. Anyway, so what would those lists look like after you learn them, and are they easier to understand?
The lists look about the same. So the top 10 words look about the same. I have a backup slide on this because I feel, I got in a big fight with the Eisenstein reviewers about this because they're like, you have a topic model paper, you have to show the topics, but they really basically look the same. So, I ran it on like 20 Newsgroup, and the perplexity was better for Sage than for LDA, but I can't really look at these topics and with a straight face tell you that they're better for Sage than for LDA. I think the advantage is that when you see this for Sage, you're seeing a much greater fraction of what the model is actually doing than what you're seeing up here, right? So LDA is assigning a probability for every word topic pair, and I'm showing you like 1% of that. Yeah.
So I think there's another kind of striking difference, which is, well, okay.
These are 5 out of 20 too, so I didn't, these are 5 topics out of 20, so I mean, they're,
Actually, I take back what I was about to say, because now that I started, the difference isn't holding up.
Okay, well, thanks.